last class we discussed about low power design. So we discussed about the parallelism pipelining and the hardware versus software trade-off. So for that we say we use like we discussed the VLIW versus superscalar architecture. Is my screen visible?
हाँ हाँ हाँ
Okay. Huh. So that we discuss, and we are saying कि we will be discussing this bus encoding techniques. Okay. So in this class, we'll go with the bus encoding techniques. We'll see how if a data is correlated, then what type of encoding we should use to minimize the power switching activity. And once the switching activity is minimized, it means your power will be less. Okay. So in bus encoding technique, hmm, so in bus encoding techniques, so what do we have? What is the goal of coding here? Like goal of this encoding here. So what do we want it? We want undesired correlation. We want to remove undesired correlation among any information or any data bits. Okay. So our bus encoding technique. Okay. So here what we are saying is we are saying we want to remove undesired correlation among information or data bits. Information bits that is encrypted. Okay. Now, why we are doing this coding? We are doing this coding for reduced switching activity. Okay. We are doing this to minimize the switching activity. Okay. So we can say कि if there is any communication data bits, okay, so if they are appropriately coded, okay, then it can reduce the switching activity. Okay. Then in bus encoding, we will talk about these things. What? We will talk about the encoding basics. Okay. Bus encoding basics. What is bus encoding? We'll talk about gray coding. And where should we use the gray coding? Then we talk about the one note encoding. And we can also go with the bus invert encoding. Bus invert encoding. Okay. Now what happened? Like, what do you mean by the bus encoding? So as I told you, bus encoding is basically what do we want is we want to remove any undesired correlation among information bits, communication bits, or data bits, whatever you call it. Okay, so we are just removing the undesired correlation. Okay, now since we are like communication data bits, we are like encoding them into some appropriate code. So that code is then reducing the switching activity. Okay. So that is the bus encoding for you. Okay. So let's say what actually happens in our design is, let's say we have our sender here. We have our sender here. This is our sender. Okay. So whenever it will send the data, okay, so it will send some n bits. Okay. So those n bits should pass through a encoding. Encoding. Correct. And after encoding, these n bits can be converted into m bits. And it will then reach to whom? It will reach to the receiver. So this is our receiver. Okay. Now this receiver first receive these m bits. So it will do what? It will do the decoding. It will do the decoding. Okay. And these decodings, so it means this decoder will take these m bits and will convert them into n bits and will give it to the receiver for the processor. Because whatever here, whatever here we want here, right? These n bits only. So in the communication path, these bits should be encoded. Okay, and that will be in the n bits. Now, 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 what happens here is there might be two cases. There might be two cases. One case is in which m is greater than n, and other case is m is less than n. Or one intermediary case is m equal to n. Okay? Okay, so what will happen is when you are saying your m is greater than n, it means these are redundant, right? This is basically redundant. Okay, and if m equal to n, these are non-redundant, and these are basically memoryless. We are just transferring one state to the other. We are just mapping one state to the other in m equal to n. So it means it is basically one to one mapping. One to one mapping. This m equal to n. Okay. In the redundant case, when m is greater than n, okay, I'm not saying m less than n. Okay. So when m is greater than n, then what will happen is this m, let's say this m is 4, n is 2. Okay. It means we are encoding 2 bits into 4 bits. So one simple example for that can be a one hot encoding. So if you say 00011011, so that is a 2 bit, that is n equal to 2. Okay, now you can code them with m equal to 4 edge this way: 00001, 0010, 0100, 1000. So this is the one example of redundant. But this is some, like, you need to remember these things, right? 00 should be mapped to 0001. 00 means the first bit should be high. Okay, and if you see the subsequent bits, if you compare this bit with any of the other bit, only one bit is getting changed, like 2 bit is getting changed. Okay, so there are less switching activity, only 2 bits are getting changed. Okay, okay, so if we can simply say in our encoding techniques, in our encoding techniques, okay, the other case is this m less than n, which is very hard to get it. Okay, so we are skipping this. This m greater than n, m equals to n, these are only the physical cases. Okay, so in our encoding techniques, we can say we have non-redundant, we have redundant. Okay, non-redundant means m equal to n. M equal to n means 1 to 1. There will be 1 to 1 map. Okay, and we call that as memoryless. That coding. Okay, now in redundant case also, we have two cases. One is m equal to n. So it means that is 1 to 1 NP. And in other case is 1 to many. In 1 to many, what will happen is m greater than n case will come up. Okay, and in this also there can be a static encoding that depends on your codings only, and dynamic encoding. Okay, so in the static encoding, the your encoder and decoder, those are memoryless. It means they're like that one to one map, or sorry, one hot mapping or gray code mapping, right? These are those things. But in dynamic coding, these are, like I told you, bus inverter coding, and these are this one, bus inverter coding, encoding. So these are those type of things. Okay, so we talk about now this gray encoding. We'll say gray coding versus binary coding. Gray coding versus binary. Now, what happens in gray coding is, so gray coding is what? Gray coding is a sequence of numbers or a set of numbers in which adjacent numbers have only one bit difference. Adjacent numbers have only one bit difference. Only one bit difference. Okay. So if you simply say binary coding versus gray encoding, so what you can see is, in binary, how do we write is? How do we write it? We have these values: 000, 001, 010, 011, 100, 101, 110, 111. So 000 is simply mapped to 000. This will be 001 only. This will be 011. This will be 010. This will be 110. This will be 111. This will be 101. This will be 100. Okay. So this one is gray. Now, if you see the adjacent bit has only one bit toggle. But here, if you see, let's say from 001 to 010, there are two bits toggle. This 0 is converted into 1, this 1 is converted into 0. So there might be some glitches where it is toggling, right? Okay, but in gray coding, if you see, only one bit is getting toggled, this second bit only. The first one is still there. So that is the gray coding. So where it is useful? So this gray coding is useful when the data is sequential. It means you know the data is sequential. Okay, and or basically the data is highly correlated. For example, instruction address, because addresses will come one after the other, right? If there is no, and like if there should not be any branch instruction or jump instruction. Otherwise, it is mostly instruction addresses are that one only, I1, I2, I3, I4. Those are sequential only. Okay, and you know number of bit transition is limited to one for sequential data. It means from one point to the other point, or one set of bits to other set of bits, only one bit of only difference between one state to the other state is only one. In that case, these are very highly correlated. Okay, but let's say there is some random data after 0, it's coming up as let's say 5. Then then the gray coding will not be that useful, right? Okay, so for random data, the number of transitions for binary and gray code both are approximately equal. Okay, so if the data is not highly correlated, then we will not say that this gray encoding is good option. Gray encoding is good option when the data is sequential and highly correlated, or we know the number of bit transition is limited to only one for sequential data. Okay, so what we can say is, we can say gray encoding
Sir, excuse me,
usually.
sir.
Yeah.
Sir, the binary to gray encoding, it's not clear actually.
Oh, you don't know how to go from binary to gray, is it?
Yes, 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 sir.
Okay. So I'll tell you one trick, okay? Okay, let's say, let me write here, binary to gray, okay? So there are logic circuit for that as well, but we are not going into that. Okay, I'm telling you the trick only. Okay, you know binary numbers, right? 0 0 0 0 0 1 0 0 1 0 0 1 1 0 1 1 1. This is the what you call binary encoding. Now in gray, you need to simply mirror the display. Let's say you have 0 1. Okay, now what you do is just mirror these values. So 1 will come here and 0 will come up here, right? I'm just mirroring these values. Okay, now put 0 0 here and 1 1 here. Okay, now do one more thing. Put mirror again. Now what will happen? 1 0 1 1 0 1 0 0. So 1 0 will come up here, 1 1 will come up here, 0 1 will come up here, and 0 0 will come up here. And now place 0 0 0 0 and then 1 1 1 1. So this is gray coding for you. Similarly, if you mirror it again and put zeros here and then ones there, then it will come up as the 4-bit gray encoding. You understood it?
Yes, yes, sir.
Okay, otherwise, or if you want to create some logic circuit, then you can map that into the K map and find that digital logic for all those circuits. Okay, okay, you got it?
Yes, sir, got it.
Okay, so basically, this is the thing. Then again, if you take it, this is mapping to this, this is mapping to this, this is mapping to this, this is mapping to this. Okay, and you are placing these values 0 0 0 in place of this, and then 1 1 1 1 here. So this is how these are just mirrors. Okay. So what we are discussing? when so what we are saying is gray encoding is useful when the data is highly correlated. So when the data is highly correlated and sequential like instruction address. Okay. Or what we are saying is we are saying number of bit transition is limited. Number of bit transition is limited to one. Transitions is limited to one for sequential data. Okay. And we discuss one more thing. If there is a random data, the number of transistors for binary and gray code both are approximately equal. For random data, the number of transitions for binary and gray code are approximately equal. Okay. Okay, you got it? Okay, and now one more thing. This gray encoding is what? This gray encoding, okay, let me write it here only. So this gray encoding is non-redundant. Non-redundant. Because here m is equal to n. Number of bits in binary and gray both are equal. And these are 1 to 1. Correct? It means this one is mapped to this. This is mapped to this is mapped to this, and this is similarly for others. Okay. So this is 1 to 1. It means it's memory-less coding technique. Memory-less 1 to 1 coding technique. Okay. 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 And remember one thing, for instruction addresses are highly correlated. So switching activity is reduced by using gray coding. And if you talk about the data, so data addresses, okay, these are not correlated. So switching activity is more and less similar to binary code only. Okay. So you can write 2 points. These are very important. Instruction address. Instruction address. Okay, so in your processor, there are two addresses. One is instruction address, other is the data address. So data can be at the different memory location, or there can be multiple things. Okay, so these are not highly correlated for the data. So that's why in data, whether you use binary or gray encoding, that is more and less similar. But for instruction address, since these are highly correlated, since these are sequential, so switching activity is very reduced by gray encoding. Okay, so in instruction addresses are correlated. Okay, this is not working. Are correlated. So switching activity is reduced by gray coding. Okay. For data, for data addresses. Okay. So these are not correlated. These are just a example I'm giving you, right? So these are not correlated. So switching activity is more and less similar in both. More and less similar to binary code. Okay. So do you have any questions in this binary to gray or gray to binary and binary versus gray? If you have any question, you can ask me. Otherwise, I'll jump to one-note coding. Now there comes one hot coding. What is one hot coding? So we remember one hot encoding is one of the bit is high. Okay. So let's say you have n states, and for n state, n bits are representing your data or your states, and one bit, like corresponding bit position of that state, is high. So that is the hot one at encoding. Okay. So in one at a hot encoding, what will happen is, let's say you have a 4 bit of data. You have 4 bit of data, 4 bit. It means in one hot, this is in binary. This is in binary. So in what? In one hot, how many bits will be there? So there will be 2 power 4, 16 bits. 16 bits will be required. So this will be the value. So it means 0th position means 0th bit will be high. If it is 0001, then it will be 1, this value will be high. So corresponding bit value will be high. So that is your one hot encoding. Okay. So what will happen in, and when we use this, so let's say we have a chip. We have 2 chips, sender chip and the receiver chip. Okay. So these chips are connected using 2 power n wires. Okay. So let's say here we have n bits only. So that has 2 power n wires. 2 power n. Means 0, 1, 2, 3, 2 power n means 2 power 4, 4 bits. So means 16 wires. In that case, what will happen is we can use this one of the coding. Okay. So what will happen is, let's say we have that same example I'm taking. We have a sender. We have a encoder here, and similarly we have a decoder here. Okay. So here we'll get the n bits since we are transferring n bits here. Okay. This is my sender. This is my receiver. Okay. Now, how many bits I'm sending is? I'm sending how many bits? Starting from 0, 1, dot, 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 2 power n minus 1. Why minus 1? Because 0 to 15. For 2 power 4 minus 1, 16, right? Since we are starting from 0, that's why we are writing this minus 1 here. Okay. Okay. So it means total 2 power n bits. It means your m will be equal to what? 2 power n. Correct? Means 16 lines will be there. So here what we can say is, whenever your 2 chips are connected using m equal to 2 power n wires. So 2 chips are connected using m equal to 2 power n wires, and a n bit data is encoded by placing one on the ith wire, where this I will be less than equal to 2 power n minus 1 that we saw, right? Is the binary value corresponding to that bit. So, corresponding to the bit pattern, and 0 on all other bits, 0 will be there. 0 on the remaining m minus 1 wires. Okay. Now, the main thing which you observe here is key subsequent bits or any of the bits. So number of transition from one bit to any of the other bit, it will be always be 2 only. So number of transition is always 2. Okay. But what happens is the number of wires that required here is increased exponential. For n, we are saying we need 2 power n wires. We can say number of wires. So again, at cost of something, we are getting something. Wire increases exponentially with the word size of data. Okay. Now, since we have talked about this one-hot coding, so we know here what happens is it is redundant. Why it is redundant? Because m is greater than n. And again, there is one-to-one mapping. One-to-one mapping. So it means this is memoryless coding technique. Okay. So you got that thing right? Right? Any questions still here? Milton, you have any questions?
No, sir.
Okay, good, good going. Okay, now we'll see bus inversion code. What is that bus inversion coding? Okay, so what happens in bus inversion coding is this is again a redundant scheme. Uh, redundant scheme means or redundant coding means कि where our m will be greater than n. Okay, okay. Now we are using this technique for other uses for other set of data. What we are discussing is we are seeing bus inversion coding. Okay, so what happens in bus? This is also redundant. Redundant coding scheme. The good part here is here m is equals to n plus 1. So it is beneficial over one hot encoding. How? Because in what? In one hot encoding, the number of bits in the receiver part or the communication channel increase exponentially, which we don't want, right? Okay. So here our m is equals to n plus 1 only. Now we'll say here what happens to the bits. Okay. So if we are saying the ith data word is SI, if we are saying ith word is SI, okay, then either SI or SI bar. If the ith bit is SI, then either we will transmit the SI or SI bar. That will depend on which would result in fewer number of bit transition. Okay, so we'll transfer this ith bit either SI or SI bar depending on which will result into the fewer number of transition. Okay, it means we need to remember the previous bits as well because then only you can determine key like 0 is fewer or 1 is fewer. Okay, so this is not memoryless. Okay, okay. So it means we can simply say in this bus, okay, we will go into depth of this. Okay, you will understand how we are deciding these things and how are we transferring those bits. So what we can say कि here our encoder. Encoder will be what? Encoder will be memory. Encoder requires memory. Encoder requires memory. Why encoder requires memory? Because encoder has to remember कि whatever bits that encoder has transmitted. Okay, so in those bits, which bit is more, either 0 or 1? Okay, so that's why encoder should require memory, and your decoder can be memoryless. Decoder can be memoryless. Okay, Okay. So how do we do that? So we are saying कि let's say we have n bit. Okay, so it will be Si minus 1. So how we'll do is we'll check the Hamming distance between Si minus 1 and Si. So how we will check is Hamming distance. Hamming distance will tell the number of bits and increase the number of ones. Okay, Hamming distance between Si minus 1 and Si. So if Hamming distance is greater than n by 2, n by 2, then we'll send Si bar. Or if it is less than, if Hamming distance is less than or equal to n by 2, then send Si. Okay, so you understood this concept, right? So I can take one example. Let me take one example, then you will understand. So let's say one example. The Si minus 1 bit is, let's say this 10110011. Okay, and the Si bit is, let's say, okay, so Si bit will be what? Since we start checking from here, so 1 only come because there is no toggling. Okay, now 0 comes. But if you count number of ones, okay, so Hamming distance is what? 1, which is greater than, which is less than n by 2. Okay, because n by 2 is what? Number of bits divided by 2, that is 4 here. N by 2 is 4 here. Okay, so that will be 1 only. It means we will send what? 1. Now you check 1. Since this bit is changing, so what we need to find? We need to send 0 only. Correct? Because Si bar now we need to send. Correct? Okay, and what will be the Si bar? Si bar will be 0, 0 and simply 1 here. And similarly, if you do it, you will get this 0, 1. And similarly for this, you will get 0, 0, 1, 0. So that will be the Si and that will be the Si bar. Okay. So if I have to make the logic diagram for this, so what it will be, you need to remember the thing. So that means you need to use the flop. Okay. So what will happen here is we'll use this XOR gate. So that will be your data input. Okay. So here your data in is coming. Okay. This data in is going to some function GIX. It will be coming like this. Okay. This is coming out of the flop. This is the clock. This is T. This is again B. This is again clock. Now we are checking for the data. This is coming out of this value. This is the in. Okay, this value is again, since it's a part. So this is the bus encoding technique. So here if you see, this part is the encoder. And here is this part is the decoder. This part is the decoder. So that is the bus inversion coding for you. Okay. Okay, you have any question in this?
No, sir. No question.
Okay, so you understand it clearly, right?
Yes, yes.
You understood the coding? Okay, so what happens is bus inversion coding is a technique that we use in digital circuits or VLSI design to reduce power consumption whenever we are sending high speed data buses, right? So what we can conclude it is a technique used in digital circuits and VLSI design to reduce power consumption on high speed data buses. High speed data buses. Okay. Okay. So in this, what will happen is here the system will compare the new data with the currently transmitted data on the bus. Okay. So here you can see we are comparing. Here you can see we are comparing the newer data with the transmitted data. This data is transmitted, right? Or you can say this is the transmitted because this is coming out of the flow. So we are comparing. Okay, so system compares the new data with the currently transmitted data on the bus. Okay, and how it compares it? It basically count the number of bits. Okay, and how it is those number of bits are basically Hamming distance only, right? So if we are saying if the number of transition is less than or equal to half the bus width, okay, then we'll say data will transmit normally. Okay, or if the number of transition is greater than half the bus width, then we'll say the data is that we transmit is completely inverted. Okay, so let me take that example. Okay, so how we are taking that example is, so let me take this example again. So let's say current data on bus is, how do I take? Okay, current data in the bus. Current data. Okay, let me write example here. Okay, so what is the current data? Current data on bus is, let's say I have 8 bits of 000000000. Okay, so this is my current data on the bus. And next data that I want to send, next data to send, let's say that is 10110001, something like that. Okay, so first what do we do? First, what do we do? We'll calculate the transition. Okay, so if we say if we directly transmit this 10110011, then what will happen? See, how many transitions are there? 0 to 1, 0 to 1, 0 to 1, then 0 to 1 to 1, 2, 3, 4, 5. 5 transitions are there, right? Right? You understood it?
One,
This
two,
one,
three, four,
this
four
one, this
transition, right?
one, this one, this one, this one. 5 transitions are there, right?
Okay,
If
okay,
we
okay.
exactly send this data only, directly send this data. So 5 transition will be there. So if I say, step 1, if I write just to tell you this, if we send 10110011 directly, then 5 transitions are there. 5 transitions are there. But we need to check this with respect to what? N by 2. What is our N by 2? N by 2 is what? 8 by 2, that is 4. Because 8 bits divided by 2, that is 4. So since we have calculated our transitions as 5, so that 5 is greater than 4. Right? So it means the bus inversion will trigger. Right? So bus inversion will trigger. It means this 1 will be converted to what? This 1 will be converted to what? Oh, basically we will invert this complete thing, right? So what we'll do is let me change the color. Let me take this one. So what do we do is we'll invert the bits. So what we will do is one will be this 1011, so it will be 0100 1100 something like that. Now if you see the number of transition, it will be less than n by 2. Okay, so if you consider the transition from 0000 to 1, so only 1, 2, 3, only three transitions are there. So okay, so you understood it?
Yes, sir, got it.
Okay, you understood it. So how we are
Yeah.
doing it? Huh? You are asking something?
No, no, nothing, nothing.
Nothing. Okay. Okay, so you got it. So that is how
Yes.
we transmitted. And if you see with these digital logic also, you will get to understand. So you have to check the Hamming distance and will compare with that. Then you will get the answer. Okay. So I hope it's clear to you. So that is the bus inversion coding for you. So if you see this coding, it will work better for smaller values of n. So if you practically see, okay, so this coding basically helps with the. So if you see this coding technique works better for smaller values of n. Values of n. Okay. So if you see for like some practical data says if this value is n equal to 2, the switching activity will be reduced by 25%. But if you go at n equal to 32, then you will realize the switching activity is reduced by 11%. Okay. We can say for larger values of n, the n-bit data bus can be divided into smaller buses. So what we can do is, let's say I want to transmit 32 bits. So what I can do is, since we know this encoding technique works better for smaller values of n, so what we can do is, we can divide that 32 bits of chunks into smaller, let's say 444 bits. Okay, so that will work for you. Okay, so for larger values of n, for larger values of n, the n bit data bus can be divided into divided into smaller groups. And each group is new text में old text coded independently. Okay. So this is the bus encoding technique for you. Okay. So you understood how we can minimize the switching capacitance through the like we can minimize the switch capacitance using these techniques. So we like in the last class we saw these techniques, right? So if you see in the minimized switch capacitance, we talk about this hardware software trade-off, bus encoding, number system, right? In the hardware software trade-off, we understood bus encoding we covered today. So these are the things. Now we go with the clock getting and see okay, how we can minimize our switch capacitance. Okay, so we can minimize the switch capacitance using, let's say, clock getting. Okay. Okay. So if you see in a processor, so the major component of processor power in clock is in any processor is clock, because clock switches 50% of the time, 0 to 1, 1 to 0, 1 to 0 to 1, 1 to 1, and each flop requires a clock. Okay. So if you somehow restrict the clock to toggle, somehow if you restrict the clock to toggle, then you'll get one of the most successful way to restrict the switching power, right? So one of the most successful and commonly used power technique is restricting this clock to toggle much, because the major component in the processor power is clock power only, because it is switching 50% of the time. Okay. So we can say, like, what I can say is the basic idea is it, we can observe that a large number of transitions are unnecessary. In the clock, large number of transitions are unnecessary. Let's say the data is not changing for 100 cycles, but still the transitions of clock will be ongoing. Okay, so it means we can observe that the large number of transitions are unnecessary. So what does that mean is, it means when we are applying a clock, it is making transition, and those transitions are always not necessary, right? Okay, so we'll find that some part of the circuit are not in use. So when that clock is transitioning, we will realize that some part of the circuit is not in use, or they are not doing any function. Okay, and their output is not used in any of the situation. So what we can shut off that, we can shut off that power. We can shut off the toggling of that clock. We can shut off the clock. It means there will not be any unnecessary transitions on the clock. Okay, and that will not affect the functionality of the circuit as well. Okay, so that is the basic idea that is known as the clock gating. Okay, so that is the clock gating thing. So what do you mean by clock gating? So clock gating is what? We know the major component of processor power is the clock power. It means because clock is always toggling 50% of the time. So what we can do is we can gate this clock. I know most of the time whenever my clock is toggling, most of the, like one of the block or many of the circuit part, the clock is unnecessary toggling. So I can provide some enable signal, and through which I can control the clock. Ki whenever that particular signal is high, then only I need to make that toggle on the clock. Otherwise, we will say the unnecessary transactions on the clock we can reduce, and that will save us a lot of power. Okay, so it means large number of transitions are basically unnecessary. Okay, so when we are applying a clock, it is making transition, and those transition are most of the time not necessary. Or particularly if we find that some part of the circuit are not in use, or their function is not the outputs are like no, their outputs are not used in any such situation. So at that time, what we can do is we can shut off that clock. That means all the unnecessary transition will be suppressed and without affecting the functionality. So that is the clock getting. And we know there are huge opportunity. There are huge opportunity to shut off circuits that are not in use. Okay, so that's where this clock getting is used. So clock getting is the major technique to reduce the switching capacitance, to reduce the switching power in low power design. So if you incorporate clock getting in your design, you are handling a lot of, or you are saving a lot of power dissipation. So you understood it. Okay, and this clock gating is most widely used for reducing the dynamic power consumption. Okay, so and we all know, right? Or dynamic power is what? Dynamic power is what? Alpha into C VDD square into F. Is alpha is switching activity. Okay, and we know clock toggles like this only 50% of the time. It means this alpha is very much. Okay, so if you reduce this thing somehow, okay, so we can reduce the power.
Sir, if we are gated clock, it only reduces alpha or reduces frequency as well.
Okay, let me tell you one thing. Let's say there is a functional block, okay? Okay, and clock is going here. Okay, now my data is something here, data in is here, and data out is here. Okay, let's say for the first cycle, for the first cycle, the data changed. Okay, so let's say I have a clock here, a big clock. Do, 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 do. Some 100 cycles are there. Okay, and my data toggled somewhere here. Okay, so let me write it this way. Data toggled somewhere here. Okay, so A to B, let's say. Okay, now after 100 cycles, the data B is remain same. Okay, and it is toggling after some 100 or something. So between this is my data in. Okay, so data out will remain same after this clock. Let's say this function block is consuming some 2 cycles. So my data out will be what? Data out will be somewhere here. Okay, so A, B. Okay, and it will remain same here. Okay, now you know for this much of cycles, for this much of cycles, this much of cycles. Okay, if you know your data input is not toggling, your data input is not changing, is it necessary to transfer this clock cycle to here? Is it necessary to, because these clock transition are then unnecessary because data one time samples here, it will remain same for these number of samples. Okay, so basically what you can do is you can provide some enable signal here and you can basically switch off these, like you can shut off these transitions. How you can do it? So if you are providing this clock or you are providing, let's say I'm writing this gated clock. Okay, I'm providing this type of clock and then it's 0 for the complete time and it started 1 here. So both this clock and this clock, they are giving us the same functionality, but at what cost? This is reducing the switching activity because the clock transition are not here. Okay, so this will reduce the power, right? So that is your thing. Understood?
Understood, sir. Who is deciding clock gating actually?
The
Which one is
designer will decide this thing. Designer who is doing the RTL or who is whoever or architecture will
no
decide
no
that. We'll
workload
go
is
more
running?
depth into.
Yeah, okay, sir.
Sorry.
If any workload is running, the clock gating
Hmm.
is required or not? It's a random workload, right? That someone will decide, right?
So they will provide. Someone will decide. I told you, right? The designer will decide. So what will
Okay.
happen is, okay, this is the clock going in. Okay. So what we'll do is the designer will generate an enable signal or some enable signal. Let's say this FBA, so A enable signal. So what he will do is, let's say I have applied a AND gate. Now this clock is going here. So clock will go into the AND gate and this enable signal is one. So whenever you know this enable is high, then only this complete clock will go here. Otherwise, we'll send 0 only. Because enable is 0, it means this clock will be 0. Gated clock. Sometimes. Okay. So we'll discuss those things in the next class. Okay. We'll see how designer will decide and all those aspects of low power design. Okay, and what is the clock getting principle? How we can improve clock getting circuit? Because it is not necessary we will use the AND gate, because AND gate will introduce some spurious activity. Okay, and or glitches. So we don't want those glitches to come and go into this functional. Okay, so I'm unsharing the screen, and from here only we'll start the next class. Okay, then bye.
Okay, sir. Thank you.
Thank you.